Welcome to the subskills for chapter 2 of trigonometry. On this video, we will be covering exponential rules, operations on polynomials, solving systems of equations using substitution, and operations on square roots. Let's go ahead. Number 1, simplify. In order to get started with these different problems, we will want to take a look at some different properties. And we're going to be employing our exponent rules. So I like to start with a simple demonstration where we look at what happens if we do something like x squared times x to the third power. Well, if we think about what does x squared mean? That's just x times x. And whereas x cubed is the same as x times x times x. And so really, we now have x multiplying by itself 5 times, or we get x to the 5th power. Now, when the exponents are small, like 2 and 3, it's easy enough to write out, but we don't want to have to do that in general. So instead, what we want to do is we want to have a rule where if we have x to 1 power, let's call it n, times x to another power, let's call it m, then what do we do with the exponents? Well, notice we would add the 2 and the 3 to get 5 in that previous example. And so our exponent will be n plus m. And really all we want to see is that if you have 2 powers with the same base, to combine those 2 powers when we're multiplying, you would just add the exponents. So let's go ahead with 1a. Negative 3x to the 4th times 2x cubed y cubed times 6y to the 6th power. The first thing I want to call attention to is the fact that we have regular numbers such as negative 3, 2, and 6, and then we have variables x and y. So our regular numbers will do the regular operation. So since these 3 quantities are multiplying, our regular numbers will multiply. So we can multiply negative 3 times 2 is negative 6 times another 6, negative 36. Now we are ready to combine any of the like variables. So here we have x to the 4th, and we're going to multiply it by an x to the 3rd. And so we keep the base the same as x, and we add the exponents. 4 plus 3 is 7. Similarly, we will do the same for our y's. So we have y cubed times y to the 6th power. So our base stays the same, y, and we add the exponents. 3 plus 6 is 9. Therefore, our final answer is negative 36, x to the 7th, y to the 9th. Now, on part B, we have the quantity 3x squared y to the 5th z, all raised to the 4th power. So again, let's explore for a moment. I'm going to take something now like x squared, and let's raise it to the 3rd power. So in essence, if we are taking something and raising it to the 3rd power, then we're multiplying x squared times itself 3 times. And now using this property that we just explored previously, now we can add the exponents. 2 plus 2 plus 2 is 6. So we get x to the 6th. Or we could have even broken this down even farther to x times x, x times x, x times x. Again, we get that x to the 6th power. So now let's figure out what is the rule if we have x to the n and we raise it to the mth power, then the base stays the same, and now the exponents will multiply. Since we can see here, 2 times 3 gave us that 6. So we'll write n times m. So let's go ahead and do this next problem. Here, first, we want to observe that because when we think about the structure of math, we have powers, then we have multiplying and dividing, and then adding and subtracting. And because we have a power over multiplying, and those are two neighbors, those two operations are in fact neighboring operations, they're just one level away from one another, we can go ahead and pull that fourth power to each of these factors. So first we have the regular number 3. So we're going to raise 3 to the 4th power. Next, we have this x squared, but raised to the 4th power. Same with the y to the 5th, raised to the 4th power, and z to the 4th power. Because we have just simply 3 to the 4th power, we can multiply that out. So 3 to the 4th power is the same as 3 times 3 times 3 times 3. And we can multiply. 3 times 3 is 9. I like to go over here. Another 3 times 3 is 9, and 9 times 9 is 81. So we get 81. And now when we have a power raised to another power, the base will stay the same. So we get x as our base, but the exponents will multiply. 2 times 4 is 8. For the y's, same thing. Y is our base. To find the exponent, we multiply 5 times 4 is 20 and bring down z to the 4th. And we are now done since each base only appears once. So our x only appears once, our y only appears once, and our z only appears once. Okay, the next problem we're going to do is really combining the skills from 1A and 1B. So first, we need to evaluate these outer powers. So again, because there's only multiplication inside the parentheses, we can bring that power into each factor. And the same with the squared. So on the first part, we're going to get 2 to the 3rd power. Then we need to raise x to the 4th to the 3rd power. And y to the 3rd, we'll raise that to the 3rd power as well. Moving on, we will get 3 squared, x squared. We'll need to raise y to the 6th to the 2nd power, as well as z to the 4th to the 2nd power. Now we're ready to simplify. 2 to the 3rd power is just 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. And now that we have a power to a power, the exponents will multiply. 4 times 3 is 12. So we get x to the 12th. 3 times 3 is 9. So we get y to the 9th power. 3 squared is simply 3 times 3, or 9. bring down the x squared. Again, multiplying exponents, we get y to the 12th and z to the 8th. Now we're ready to multiply. So regular numbers will do the regular operation, but exponents will be one step weaker. So notice our regular operation off to the right here, our regular operation is multiplying. And so one step weaker will be adding. So our regular numbers will multiply. 8 times 9, 72. But our exponents for any one base will add. So 12 plus 2 gives us that x to the 14th power. We have y to the 9th times y to the 12th. So our base is y, and our exponent is 9 plus 12, or 21. And last, we'll bring down that z to the 8th power. So our final answer is 72, x to the 14th, y to the 21st, z to the 8th. Now we have one more exponent rule that I'd like to explore, and that is if we have x to the 2nd over x to the 3rd, or x to the 3rd over x to the 2nd. I actually want to explore both of these. So on the first one, x squared over x cubed, let's just write those out. X times x up top, x times x times x on the bottom. So here our exponents, our x's will cancel out because x divided by x is just 1. And another one will cancel out. We get 1. And we're left with just an x on the bottom. So we keep the 1 as a placeholder up top. Similarly, if we look at x cubed over x squared, again, just writing it out. Again, x over x is just the same as 1. And this time we are left with x, but the x is on the top. And x divided by 1 is just x. So what I like to do is, well, the rule is if we have an x to the m over x to the n, then we get the value, or our base is still x, but our exponent, we will subtract the exponents to get m minus n. What I like to do, instead of always subtracting the top minus the bottom, instead, I like to just subtract 3 and 2, no matter what. In either of these cases, I would just subtract 3 and 2 to get 1. And then I decide, well, where will my x's be left over? Well, on the first example, x squared over x cubed, I have more x's on the bottom. So the extra x's will be left on the bottom. Whereas in this x cubed over x squared, I'll still be only left with 1x, but now since I started with more x's on top, the remaining x will be left up top. So let's put this into practice. We're going to take the quantity -3x to the 5th, all raised to the 2nd power, divided by the quantity 2w to the 3rd power, y to the 4th power, all of that raised to the 3rd power. So first step, we will bring in our powers. Here I get -3 to the 2nd power and x to the 5th to the 2nd power. On the bottom, or in the denominator, we'll get 2 to the 3rd power, w cubed to the 3rd power, and y to the 4th to the 3rd power. Now, on the top, we get -3 squared is the same as -3 times -3, which gives us a +9, since a negative times a negative is a positive. We get 9x to a power, and to find that power, we're going to multiply 5 times 2. And here, this is one of those cases where our overall operation is power. So regular numbers like that -3 will raise to the second power. But when we're taking a power to a power, our exponents go down one step. And so now we'll multiply. 5 times 2 is 10. So we get x to the 10th. In the denominator, 2 to the third power, as we saw before, 2 times 2 times 2 is 8. And we'll get w raised to the 9th power, multiplying 3 times 3, and multiplying 3 times 4 to get y to the 12th power. Now, I just realized that this concept over here actually doesn't apply because 9 and 8 don't have any common factors, and all of our bases are different variables. So we actually will not be able to simplify any further. So we are done. So we get 9x to the 10th power all over 8 to the 9th power, y to the 12th power. Okay. Example 2. Now I'll show all of these just to see, but then I'll zoom in. First, I want you to notice that we have different expressions. So on part A, we have x. Some of our terms have variables like x, others don't. Then we even have x to the second power, or here, x to the third power. These are all examples of polynomials. So let's just explore that for a moment. What is a polynomial? It's where we have our variable is the base. So we could have something like 2x squared. That's a monomial because there's one term. Or we could have something like 2x squared minus 1. Now this is a binomial because these have two separate terms, but they cannot be combined since this term has an x squared and that does not. And then the last one we name is something like 3x to the 4th minus 2x plus 1. This will be a trinomial because there are 3 terms. After that, once you have more terms, we just call those in general polynomials. And these are all polynomials, they just have special names. Again, 1 term monomial, 2 terms binomial, 3 terms trinomials. So this first one, we take a look and we observe that the 2x, the first term is 2x and it has an x. And the third term, -1/6x, also has an x. So we can now combine 2x minus 1/6x. And so let's go ahead. Oh, one other thing I wanted to mention over here, back to the terms. One key feature is terms are separated by addition and subtraction. So even looking up on 1C, that actually is 1 term because there's no adding or subtracting. So here, let's take a look at back to 2a. So if we have 2x minus 1/6x, now we need to be able to subtract 2 minus 1/6, which means that to be able to subtract 2, or in this case, a whole number minus a fraction, we could find common denominators. So to write 2 as a fraction, I could write it as 2 over 1. And then the common denominator between 1 and 6 is 6. So I can now multiply top and bottom times, I will multiply 2 over 1. I'll multiply top and bottom by 6 to get 12 sixths, and I'll subtract 1 sixth. And take a look here, 12 sixths. Well, if I divide 12 by 6, I do get 2. And so that's why 12 sixths is equivalent to 2. Now I can subtract 12 minus 1 is 11, and my denominator stays the same. So I get 11 sixths. So 2x minus 1/6 x gives me 11 sixths x. Next, we are ready to combine the constants. So we have negative 1/3 plus 1. Let's go and see what we get there. Negative 1/3 plus 1. Again, we need a common denominator. So we can rewrite 1 as 1 over 1. And our common denominator between 1 and 3 is 3. So the bottom will multiply top and bottom by 3. And we get the negative 1/3 plus 3/3. And we'll add those together. And notice negative 1 plus 3 is positive 2, and the denominator stays the same. So we will just bring down plus 2/3. And I made it a plus because our 2/3 was positive. Now, in trigonometry, as we move farther along, and especially as we move into radians, we will often be adding or subtracting the numbers 1 and 2. So it's really awesome to know 3/3 is equivalent to 1, or 6/6 is equivalent to 1. And even one step further would be knowing equivalences for 2. So in this case, 12/6 is equivalent to 2. Or we might have 8/4 is equivalent to 2. So just noticing those patterns at this time. So our final answer will be 11/6 x plus 2/3. And we cannot combine those two terms because the 11/6 term has an x and 2/3 does not. All right. Now we're going to, in this case, subtract two different polynomials. And now we're getting into higher power. So notice there's x squareds and x's and constants. Now, one strategy to handle subtracting a polynomial is to just simply distribute that negative to all of the terms following that subtraction. So the shortcut could be to simply change the sign of everyone in the parentheses. So it will become a negative x squared, a positive 2x, and a negative 7, and now I add them. So I encourage that. I welcome that. I have no problem if you do that, but I will show the extra step for those of you that like to be a little bit more careful and write things out thoroughly. So the first polynomial, in this case, a binomial, 3x squared plus 4x just comes down. And then I will distribute this negative to each of the 3 terms in that trinomial following that subtraction. So I get minus x squared. And that negative times a negative is a positive 2x. And then a negative times a positive is a negative 7. So it behaves much like a negative 1. In fact, you could even put a negative 1 in front and multiply. So now we're ready to combine like terms. 3x squared minus 1x squared, if you like that. We get 2, and just like our denominators stay the same, the exponents will stay the same as well. So we get 2x squared. And it's kind of like I have 3 of these and I'm taking away 1 of these. So I'm left with 2 of these, and these are x squareds. Similarly, we have 4x plus 2x is 6x, and it's positive, so I write a plus. And then the -7 is the only constant, so I'll just bring it on down. So my final answer here is 2x squared plus 6x minus 7. Again, we cannot simplify any further because that first term has an x squared and the second term has an x, the third term's a constant. So they are not like terms. Next, we will go ahead and multiply. So this is where some of our exponent rules can be applied, but we're going to go ahead and take this whole term out front, that whole monomial, and we're going to distribute it into each of the 3 terms. And that will be through multiplication, since that's the operation between the 5x cubed and those parentheses. So we will go ahead and regular numbers, we're going to do that regular operation. So 5 times 2 is 10. But exponents will add because we're multiplying now x cubed times x squared. And so we get x to the 5th power since 3 plus 2 is 5. Now we'll multiply 5x cubed times -3x. So 5 times a -3 is -15. And the exponents will add. We have x cubed, and we could put a little 1 there if that helps us. So 3 plus 1 is 4. We get x to the 4th power. And last but not least, when we multiply the 5x cubed times 1, we get plus 5x cubed. And that is it. Whoops. Let's try that again. There we go. Okay, so the last type here is going to be multiplying 2 different polynomials. Now, in this case, we have a binomial times a binomial. So some of you will have learned this as FOIL, and that is great. Keep going with it, no problem. I like to think of it just a little differently, only because I think it generalizes nicely. I like to think of it as 2 teams giving high fives to one another, like on a soccer field, a kid's soccer game at the end. So really, it's that this term right here has to high five or multiply by each term in that other team. So the 3x will end up multiplying by the 5x and by the -6. Similarly, the -2 will also need to multiply by both the 5x and the -6. And so you'll notice, and for those of you who just need a quick reminder on FOIL, it's you multiply the first, then outer, first, then outer, then inner, and then last. The FOIL method only works for a binomial times a binomial, whereas if you just make sure that every term from the first factor multiplies by every term on the second, that will work even for bigger polynomials. So let's go ahead and we'll start with the 3x and multiply that first by 5x. So 3 times 5 is 15. X times x is x squared. And then we'll multiply 3x times -6. So 3 times -6 is -18. Bring down the x. Similarly, -2 times 5x is -10x. And then -2 times -6 is a positive 12. A negative times a negative is a positive. And last but not least, we'll just combine like terms. The 15x squared comes down, but we will Combine negative 18x minus 10x gives us negative 28x. And then we bring down the 12. And there we have it. We get 15x squared minus 28x plus 12. Again, these are all, none of these are like terms, so we are done. Okay, we are going to do just a quick look at solving systems of linear equations using substitutions. Now, there are application problems in trigonometry that require substitution. However, farther down in the semester, we'll also be using that whole idea of substitution to simplify identities or simplify trigonometric expressions or prove identities. So this is a skill that the substitution will be applied to solving systems of linear equations, but it also can be applied to trigonometry as well. So let's look at the first example. We have y equals 7x plus 3 and y equals 5x minus 11. Again, we have two variables here. So we have an x and a y, but we're trying to find an xy combination that works for both equations. So if you look, the first equation alone, this first equation alone has infinitely many solutions. This second equation alone has infinitely many solutions. However, in this case, together, there's only one solution that works for both of these equations. So let's take a peek. The first step in using substitution is we want to isolate one variable. And once we isolate one variable, we will go ahead and plug that into the other equation. And it's important that it's the other equation. We can't skip that. That's very important. And then we'll solve for a variable. You'll see something cool happens at that point. Then once we have one variable, then we'll just solve for the other variable. Okay, so let's take a look for A. If we're trying to sign by itself. So for step one, it's actually kind of done for us. We're going to isolate y equals 7x plus 3. So y is isolated. So we are good to go. Now for step two, we need to plug that into the other equation. So in this other equation, wherever we see a y, we can replace it with 7x plus 3. And then copy down the rest equals 5x minus 11. Another way to think of it in this situation is if y equals 7x plus 3 and y equals 5x minus 11, then 7x plus 3 must equal 5x minus 11. So now we have a linear equation, and what's really cool about this is now we only have one variable. So we're back to old news. Let's get all of our variables on one side. I will go ahead and subtract 5x from both sides. And now I have 2x plus 3 equals negative 11. We're trying to isolate the x, so I'll subtract 3 from both sides. We get 2x equals negative 14. Divide both sides by 2. And we're left with x equals negative 7. Now, in some of the equations we've already solved, that would have been your final answer. However, in this situation, our original problem had an x and a y. So we now need to go ahead and solve for that other variable. And I can plug it into any equation that has both an x and a y. I'll go ahead and plug it into the first one. So 7x, but we now know that x is -7, and then plus 3. So order of operations, we multiply 7 times -7 first, -49 plus 3, we get -46. So our final answer is -7 for x and -46 for y. And we can actually write those as an ordered pair, x, y. -7, -46. Okay, B is a little more complicated. In fact, the way that the first equation is written is actually not even linear in form. It's actually a rational expression as it's written, but our methods still apply. So we're going to choose one variable to solve for. So let's take a peek, and I'll go ahead in that first equation, let's solve for h. So I'm just copying it down. Now, if I want to solve for h, really, I do not like this x minus 2 in the denominator. So to cancel out dividing by x minus 2, I can go ahead and multiply both sides by x minus 2. So on the left, my x minus 2's cancel, and I'm just left with h. And on the right, I can distribute the 4 to get 4x minus 8. Now, for the other equation, let's take a look. I have h minus 2 equals 2x. Now to get h by itself, or I'm sorry. So now let's take a look. We have solved for h. That was step 1. And now we're going to go ahead and plug that into the other equation. So I'm looking at the other equation as h minus 2 equals 2x. And wherever I see an h, I'm going to replace it with 4x minus 8, because we know that h has to equal 4x minus 8. So I'm going to plug that quantity in. So I get 4x minus 8, then I write the rest out. Minus 2 equals 2x. And now, combine like terms. On the left, I get 4x minus 10 equals 2x. And I have x's on both sides again. So I'll go ahead and subtract 4x from both sides in this situation. And I get -10 equals -2x. Dividing both sides by -2, we get x equals 5. And again, just like before, we want to make sure that we solve for all variables. So our original system had x and h. So now we need to solve for the other variable. We need to find out what h is. And I like to use that whatever equation we solve for in step 1, since h is already solved for. So instead of putting x, now I'll put 5, because we found out that x will equal 5. And so 4 times 5 is 20 minus 8. 20 minus 8 is 12. So in this case, because it's an x and an h rather than x and y, it would also be fine just to leave it as x equals 5 and h equals 12. Okay, so that is a quick introduction or review of solving systems of linear equations using substitution. We'll go on to our last set of subskills, which is operations on our square roots. So as you can see here, we're going to add, subtract, multiply, and divide expressions that contain square roots. So just like when we add or subtract fractions, we need a common denominator. When we add or subtract square roots, in order to combine them, they have to be the same square root. So we can add a square root of 2 to another square root of 2, but we cannot add a square root of 3 to a square root of 2. So let's see this in practice. So for number 4a, we have the square root of 28 plus the square root of 63. Now, as they're written, these cannot be combined at all because the square root of 28 is not the same as the square root of 63. However, we could try to simplify both of these square roots. And if they both reduce to a common square root, then we might be able to add them together. So let's go ahead. Remember, we like to think of all of our perfect squares or our square roots. So square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. And square root of 25 is 5. So these are good to have kind of at our fingertips. So if we employ this method of, okay, do any of these perfect squares go into 28 evenly? So does 4 go into 28 evenly? Yes, it does. Then we can just break up our square root of 28 into square root of 4 times square root of 7, because 4 times 7 is 28, which is nice because now we can find the square root of 4 is 2, and then we're left with rad 7. Now, if you're ready to give it a little practice, try that on, you might push pause and try to simplify the square root of 63. So does 4 go into the square, does 4 go into 63 evenly? No, but 9 does. So now we'll break up the square root of 63 into the square root of 9 times the square root of 7. And now the square root of 9 is 3, so we get 3 rad 7. Now both of these were reduced to be multiples of the square root of 7. So if we have 2 of these plus 3 of these, we now have 5 of these. And these are rad 7s. So our final answer is 5 times the square root of 7. So let's go ahead with B. I'll also go ahead and show the square root method, the method using the factor trees. So I'll show it with one of them, but you're welcome to use it more. If we do the factor tree for 20, we could break it up into 2 times 10, and then 10 is 2 times 5. And so what happens there is our pairs, so the 2 times 2 comes out in front of the square root, and the singletons, the 5, is left inside. Or using the method I've been showing otherwise, we could break it up to rad 4, rad 5, which is 2 rad 5. Okay, now the denominator is 3. And then for the rad 45, same thing. I could do factor trees. I could do either factor trees, or I could break it up into rad 9 times rad 5, or we could get 3 rad 5 all over 2. So now we have like radicals. We have rad 5 for each of those. However, we do not have common denominators. So we have to find what is the common denominator between 3 and 2, and that's going to be 6. So if we want the denominator to be 6 on both of these fractions, the first fraction will multiply top and bottom by 2, and the second fraction will multiply top and bottom by 3. So for that first fraction, we get 2 times 2 is 4, and then bring down the rad 5. On that second fraction, we get 3 times 3 is 9, and bring down the rad 5. And now we can add, or in this case, subtract those. We have 4 rad 5 over 6 minus 9 rad 5 over 6. So we could subtract what is 4 minus 9. We get negative 5, and the rad 5 stays the same, and the denominator stays the same. So our final answer is negative 5 rad 5 all over 6. All right, so one more where we have some simplifying. Now, I will, rad 32 can be a little tricky when you're simplifying square roots. So I will go ahead and show a couple different methods. So one option is if we happen to notice, if we look at our perfect squares, does 4 go into 32? It does. But if we happen to notice that something even bigger, a bigger perfect square goes in, then we could do it that way. But let's first just go ahead and I'll show it to you if we just did rad 4 times rad 8. Well, if we do it that way, we'll see that rad 8 can actually be broken up even further because the 4 can also go into the rad 8 again. So we could break that up into rad 4 times another rad 4, rad 2. And so that's going to give us that 2 times 2, rad 2. And so to finish that off, we will multiply 2 times 2 is 4, rad 2. But notice if we would have done rad 16 times rad 2 in one step, we could have gotten right to 4 rad 2. Oops, I wrote rad 6 over here, 4 rad 2. Now, for the next one, we'll go ahead and simplify rad 18. So here, looking, 4 doesn't go in evenly, but 9 does. So I could break that into rad 9, rad 2. Or we get minus 3 rad 2. And last but not least, we can do the same for rad 12. We can do rad 4 rad 3 or plus 2 rad 3. Now we have 4 rad 2 minus 3 rad 2 plus 2 rad 3. So we can combine some of these, but not all of them. Since the first two have been simplified into multiples of rad 2, we can go ahead and subtract 4 rad 2 minus 3 rad 2 is going to be just 1 rad 2, or we'll write that, or I'll write 1 rad 2 to start, because 4 minus 3 is 1. And then bring down the plus 2 rad 3. Notice this rad 2 and this rad 3 are not like radicals, and they cannot be combined. So our final answer, we'll just drop that 1. So we get rad 2 plus 2 rad 3 is our final answer. Okay. Now, multiplying. Just like when we multiply fractions, we can multiply any fractions together. They do not have to have common denominators. Similarly, for radicals, we can multiply any radicals together. So one option would be multiply first. However, I think it's much easier to get our numbers as small as possible first, and then we'll multiply afterward. So I'll go ahead with that method. And let's go right ahead and we'll first simplify 24. Again, 4 goes in evenly. So I'll go rad 4, rad 6, and 4 goes into 20 as well. So rad 4, rad 5. And now we get 2 rad 6 times 2 rad 5. And now we can multiply. The 2's are outside the radicals, so we can multiply those. 2 times 2 is 4. And the 6 and the 5 are both inside the square root. Since it's multiplying, we can actually multiply those together. So 6 times 5 is 30, and we get rad 30. And we still should check, does 4 go into 30? No. Does 9 go into 30? Nope. Does 16 go into 30? No. And we can stop there since 16 times 2 is already bigger. 30, it's 32, which is already bigger than 30. So that's our final answer for rad 30. So notice the difference here. When we're adding and subtracting, you can only combine like radicals and the radical stays the same. But when we multiply, anything can multiply. Similar with division. So for E, you could choose to rewrite this as, or we could choose to rewrite this as rad 2 divided by 3, and then divide that using that division symbol by rad 5 over 7. Or we could also have skipped that step and just say we take the top fraction, flip the denominator, and multiply. But if it helps to write it this way, so this is, that's a more traditional way to write division with fractions, is using that division symbol. And then after that division symbol, we flip and multiply. So either way, now we're ready and we can multiply straight across, and we get 7 rad 2. Notice I did not multiply 2 times 7 since the 2 was inside the square root and the 7 is not. Similarly, on the bottom, we get 3 rad 5. Now, my final answer should not have square roots in the denominator, so I'll multiply top and bottom just by rad 5. The 3 is not the problem. And we get 7 rad 10, because it's multiplying, so we can multiply rad 2 and rad 5. And on the or just 5, but the operation between them is multiplication. So our final answer will be 7 rad 10 all over 15. And notice, even though the 10 and the 15 normally could be reduced by 5, we cannot simplify those two because the 10 is inside the square root and the 15 is not. All right, so last example for these subskills. Let's go ahead. We're going to combine what we were just doing up above when we were multiplying polynomials. It's similar, but the first thing we want to do is simplify our square roots. So whether we use factor trees or just rewriting them in terms of a perfect square. Now, 4 doesn't go into 50, 9 doesn't, 16 doesn't, but 25 does. So rad 25, rad 2. And then 4 doesn't go into 27, but 9 does. So we got rad 9, rad 3. And just like before, we got rad 4, rad 3, 4, rad 12. And so we have 5 rad 2 minus 3 rad 3 is the first part. And then we have 3 minus 2 rad 3 in the second. And now back to multiplying. We want to make sure this 5 rad 2 multiplies to both the 3 and that 2 rad 3. Same thing, we're going to have that negative 3 rad 3 multiplied by both the 3 and the 2 rad 3. So let's go ahead. We get 5 rad 2 times 3, 15 rad 2. Then 5 rad 2 times negative 2 rad 3, negative 10 rad 6. Now these two, negative 3 rad 3 times 3, we'll get negative 9 rad 3. And last but not least, negative 3 rad 3 times negative 2 rad 3, we'll get a positive 6 rad 9. And now we're ready. Notice rad 9 is just the whole number 3. So 6 times 3 is 18. And let's bring down the rest and see what we can combine, if any. So the first term has a rad 2, second term has a rad 6, third term has a rad 3. Last term is just a constant with no radicals. So these are all unlike radicals. So we are done. Our answer is 15 rad 2 minus 10 rad 6 minus 9 rad 3 plus 18. And that does it for our subskills for chapter 2.